We continue the discussion of congestion control, how it is implemented in the internet. This is what we have seen so far. Congestion control in the internet is implemented in TCP, consists in additive increase, which is incremented, roughly speaking, by one segment, one TCP segment every round trip time, as long as you receive positive feedback, which means there is no loss on the TCP connection. When there is a loss, the congestion is halved, divided by 2, and there is a short slow start phase during the recovery. The reason for slow start is originally because when you start a TCP connection, you don't know what state the other connections that are competing on your network portion are, and therefore you want to not start from a maximum, from a high value, but start from 0 or the minimum value, 1 or 2 TCP segment sizes, and very quickly move exponentially fast until you see a loss, in which case you will have the window and etc. until you don't see a loss and you reach your target window. As we have seen, this is a management of transients. Why do we do slow start when there is a loss? Where in principle we should not. Originally there was, and this is what I've shown in the previous graph, but most losses are detected by different mechanisms. Losses are detected by different mechanisms. Most losses are believed to be detected by receiving duplicate ACKs. So the designers of this congestion control made the following reasoning. If there is a timeout for detection of a loss, it's something severe. Because in principle, when there is a stream of packets and acknowledgements and there is an occasional loss, you should detect it by receiving duplicates, by fast retransmit. Therefore, we differentiate the treatment of what happens to TCP congestion control by saying if there is a timeout, we believe it's a hard thing happening, so we interpret this by caution and we do slow start. We think it might be that the network is much more congested than we originally thought because things have changed, for example. Things have changed because of a sudden surge in traffic or because there was rerouting somewhere. In the other cases, we want to strictly do AIMD without a slow start phase. So that's the first step of the reasoning. However, and this gives us a new algorithm, fast retransmit and fast recovery, where the idea is we don't go into slow start. We stay at the window we are, divided by 2. So if I had a window of 10 packets, I have a loss that's detected by fast retransmit. I will set the window to 5, in theory. In fact, what we would like to do is set the rate at which TCP transmits to half the rate it was before the loss. And in order to do that, we do it by manipulating the window, which is only approximately true. It's true in particular if there is no loss on the connection. But when there is a loss, if you have lost, for example, packet 5 of your window of 10, or say if you've lost a packet, you have a window of 10 and you've lost one of the first 5 packets. If you have the window, if you reduce the window by 5, now your window size is 5, you have sent already a large number of packets that may even be outside the window. And as a result, it may be that your window is blocked, you cannot send anything at all. If your window is 5 and the packet that has been lost is more than 5 packet numbers ago. I'm reasoning in packet numbers, TCP reasons in byte numbers, but let's omit that for a second. In other words, what happens is if you dramatically reduce the window size by half, it may be that you're blocked from sending, which means the rate that you're achieving now is 0. In other words, we see there is a mismatch between the rate control that we would like to do and manipulating the window. We could do things differently by forcing a rate control that exists in some industrial environments, for example, but that is not done in the internet today. Instead, we try to fix it heuristically, and this is what fast recovery is done. So fast recovery does the following. We say, yes, we will have the window, but we are aware that when there is a loss, in fact, because of the very principle of how sliding window works, in order to continue being able to send packets, we need to continue with a large window. So this is what fast recovery does. The congestion window is allowed to continue to increase until the loss is repaired, to avoid this side effect here. And when the loss is repaired, then we go back into the mode, the normal mode, with a window which is equal to the target window. That gives the following algorithm. When we detect losses by fast retransmit, we cache the current value of the window and put it in the target window, which is 0.5 the current size. And then we increase the target window by 3 if we have received 3 duplicates. So this is a parameter that depends on how many duplicates we consider for triggering fast retransmit. And then we do exponential increase of the congestion window size until the loss is repaired. Not until we reach congestion window equal target window, because here congestion window is larger than the target window. But until the loss is repaired, and when the loss is repaired, then we do things as usual. We start, but with a congestion window which is half the target window, the previous, so, which is the target window. So in the hypothetical case I gave before, where you have lost one of the first packets in the first half of the window, when you have repaired the losses, then your window can continue to move. So even if you have a smaller window, you're able to continue to send at a rate which, if the formula we gave before applies, would be what we want, half the rate. Here is an example. We're focusing on the sender on the left, which sends packets. Packet number 2 is lost, is detected after receiving 3 duplicate ACKs, which is here at this point in time. So the target window, which is equal to the congestion window, in other words, there's no target window in the normal phase, in the congestion avoidance phase. But here we detect this loss and we set the target window to half the value of the congestion window we had. But the congestion window becomes the value of the target window plus 3. Now, why 3? Well, not very clear, but by simulation it works. And therefore, now this sender can send packets. Which packets can it send? When we've seen that it's packet 200 that had been lost. Now, because the window is large enough, starting from 200, it can send it. It can even continue sending another one. And when this one has been received and ACKed, that's the end of this phase, we will move the congestion window to 400. And we see that in the interim phase, we continue sending because we continue increasing the congestion window by this algorithm that will allow us to continue sending. At which rate are we sending exactly? It's very hard to tell, actually. The concept of rate is not an instant concept. It's defined over a window of time. You count how many bytes have been sent divided by the size of the window. So instantly, it's very hard to say, but qualitatively, we see that with this principle, the source has been able to continue to send, probably not as fast as it was sending before, because there are losses in the window, so the source cannot send as much as if it would, cannot send a full window. But it can continue to send, and in particular, it can continue repairing the loss by a retransmission triggered by fast retransmit. If we would not do that, if we would simply have the window here, then it would not be possible to send this one. So we would need to, it would not be possible to continue to send this one, sorry. So we would need to, we send one and then we are blocked, which is considered not desirable in this case. Yes?
So basically, if you did not increase the congestion window, you could retransmit 201 to 301, but 751 to 801 you could not.
Correct. You could not. You could not.
So he acts those.
Exactly. Exactly. So we would be saying we allow perhaps the retransmission, but we do not, we stop the source. Once it has retransmitted, it has to wait until the retransmission is repaired. This is not hard science. This is just the way the most frequent version of TCP, I'll talk about which versions exist of TCP, is doing. Let me skip this one as we need to move on. So if we come back now to our original problem, we want to do congestion control in the internet with TCP. Now what is the question? What does TCP really do? We have seen that in order to design the basic principles of TCP, which are, if we ignore many of the small details, it's essentially additive increase, multiplicative decrease. This has been justified by a very simple network scenario. So now let's go back to the original network scenario that we saw last week and the week before and ask the question, what is TCP, what is happening in the internet if all sources are doing congestion control with TCP? What do you think? What's your guess? Is TCP implementing max-min fairness, proportional fairness, or none of the above? It's a guess, so you don't need much time. I close the poll in 5 seconds. I close the poll now. And the majority has become cautious and thinks none of the above, which is a very safe answer. Many people believe in proportional fairness and a few in max-min fairness. Well, we will see in, with a few more details in a minute some formulas, but the answer is none, strictly speaking none, but probably a very good approximation of proportional fairness. And if we want to be accurate, is something between proportional fairness and max-min fairness. Now, there are many caveats to this that are given here. We can show with relatively crude approximations that for long-lived flows, flows that are long enough so that the little blurps that occur during the initial slow start can be ignored, for example, then it is true that TCP is implementing a form of fairness that is almost proportional fairness because it is in fact maximizing a utility function that is given by this strange formula, arctangent of x. X is the rate times tau. Tau is the RTT, rescaled by some parameter. Why that? You can read in the lecture notes the derivation of this. It consists in analyzing the algorithm that TCP implements, a bit like we did for the additive increase, multiplicative decrease, but approximating the dynamic of this algorithm by an approximate solution of a differential equation. That's called the method of the differential equation. There's a theory about that that's explained in the lecture note. And if you look at that and the thing is long enough, it is as if you would be maximizing this function. What is this function? Well, I'm plotting it here. Arctangent is a function that looks nicely concave. I plot for comparison the log. And what we can see is that arctangent is similar to the log, but is a bit more skewed here. So in some sense, it's closer to something like the red. If you remember max-min fairness, we can interpret it as the limits of utility fairness when the utility function is like the red curve here. So arctangent is between the log and the red curve. The red curve, like the arctangent, has a limit when the x-axis goes to infinity. The y-axis of utility function do not matter. It's only the relative value of one utility function and the other that matter. If you maximize the utility of everyone, and if you double the utility of everyone, you will have the same equilibrium point. So what matters is not the absolute value, but just the shape of the curve. The log goes to infinity when x goes to infinity, very, very slowly, but still it continues to increase. This will not. So if the value saturate of the limit of the value saturates when x goes to infinity, that means that a network, an optimizer that's trying to optimize this, will not try very hard to give very large rates to some flows, because the increase in utility is negligible. In the log, it will not try very hard, but it will try a bit harder than this. So this is why we say that as a first approximation, we can think of TCP implementing as a very crude first approximation proportional fairness. And if we want to be a little bit more accurate, we could say if you compare the max-min fair allocation and the proportionally fair allocation, what TCP does will be between the two, will be an average of the two. So that's the first thing we can say. Now with a caveat, of course, this is true only for sources that have the same RTT. If sources have different RTTs, then the formula will introduce a bias that we will discuss more now. So one way to reason about it is to look at the formula of the utility fairness here. Now, this formula is a function of the round-trip time tau. It's a bit weird to find how it depends on the round-trip time, because there is 1 over tau that is a decreasing function of tau, and arctangent tau, which is an increasing function. So how does it behave with respect to tau? We can ask MATLAB or Wolfram to plot it for us, and we see that it is in fact decreasing. It's a decreasing function of tau. So here I'm plotting the value of the utility function as a function of the round-trip time. So the utility is a decreasing function of the round-trip time. What does that mean? Well, to make sense in a more detailed way of this question, let me re-ask the question in this specific setting. Here, I'm considering two sources that are sending traffic to a given destination, and they're competing for the same bottleneck. And one of the sources, S1, has a round-trip time of 20 milliseconds, the other 60 milliseconds. So those two sources have, I assume the bottleneck is here, so those links are very high capacity, 10 gigabit per second, and this one is 10 megabit per second here. So the only difference between the two sources is their round-trip time. If they use TCP, TCP will maximize the utility of each source, the utility being given by the formula we saw before. What will happen? Which will happen to the rates? Will they get the same, or will one of the two receive a higher throughput? I close the poll in 5 seconds. And everybody practically believes that S1 will get a higher throughput, which is correct. To understand why, well, we can reason about the utility. Since the utility of S1 and S2 differ by this tau here, S1 has a smaller RTT, so for a given rate, the utility of giving the same rate to S1 and to S2 is higher if I give this rate to S1. So if I'm a social optimizer, I'm trying to maximize the total utility. If I give the same rate to S1 and S2, the utility is higher to S1. So I will give a higher rate to S1, because if I would give the same, and then I'm not maximizing my utility, I can increase the rate of S1, which will increase its utility by a large amount. will decrease the utility of S2 by a small amount because the utility of S2 is much smaller anyhow. So the optimum, which will be the utility maximization, will result in a higher rate being given by S1. The optimizer doesn't care very much about S2 because it has a small weight. Well, that's a bug in TCP. It's called the bias of TCP against long RTTs. If you're competing with someone that is competing for the same bottleneck and you have a larger round trip time, then you are not being handled fairly. This happens in the small example we gave today. It happens also, for example, if you are competing with a server that's in California with someone who is in California, and you are here, then your round trip time is much larger. So if the bottleneck is the server, and if you have a high-speed internet, if the bottleneck is the server, which is practically impossible to avoid having the bottleneck in the server if you have a large number of people going to the server, then you receive less throughput, simply because your round trip time is larger. Now, some people say it's fair, but since we have done the theory of fairness, then we know what fairness means. I mean, proportional fairness would, in general, will give you less to you than to somebody who's sitting close to the server because you are using more network links. This is true if the network is the limiting factor. And this is a desirable property of proportional fairness. If we have a network which is scarce resources, like some 3G or 2G telephone cellular networks, you want to share it fairly, and if somebody has a very, very long connection, it makes sense to give a little less to that one because you can give so much more to everyone else. That is a desirable bias against those who use more, and it's called proportional fairness. Now, of course, most of the time, if you have a large round-trip time, it means that you have it's because you are using more network links. So that, in some sense, there is often a collision of why you get less. You get less because of the proportional fairness, because TCP maximizes a utility that is almost equal to proportional fairness, but also because of the RTT being larger. Now, TCP has those two effects. One is desirable, the first one. The second is not. So you're penalized twice if you have a long RTT and the network is congested. And if the network is not congested and you have a long RTT, but only the server, for example, is congested, then you will get much less throughput. And it's impossible to fix unless we radically fix TCP, which is not on the agenda of anyone today. We have seen there is another problem with this congestion control. Not only the bias against long round-trip time, there is also another problem, which is that congestion control interprets losses as negative feedback. Now imagine you are here downloading content from a very remote server, California, or even worse, New Zealand, and you do it over Wi-Fi that once in a while has a non-negligible loss rate, plus a long round-trip time, then it's going to be very hard for you. You will be competing with others, and you will always get a much, much smaller share than others. Even if your Wi-Fi is high speed, even if the network you're using is a high performance network, because of losses plus larger round-trip time, you will get bad performance. This is why a business has emerged called content distribution network. A content distribution network solves the problem by saying, well, after all, it's impossible to serve large number of customers very, very far away. The internet is broken in some sense. The congestion control in the internet is broken. So we fix it by putting the content close to you. So chances are if you go to a very popular server that's in California, in fact, you're going to a cache or a replicate of it that is more local here. So it has given some business opportunities. If we look at the mechanic of it in detail, we can reinterpret the bias against long round-trip time by looking at the additive term. TCP is doing additive increase, multiplicative decrease, but how much is the additive increase term? Well, it's one packet, one MSS per RTT, per round trip time. So if you have a large RTT, your increase term is much smaller than someone else that has a smaller RTT. So that is another way to interpret this bias. We can go one step further and see that, in fact, there is a physical formula for the performance of the internet that is called the TCP loss throughput formula. This loss throughput formula is addressing the question, can I relate the loss rate, the rate at which we receive negative feedback, which in TCP is simply the probability, is interpreted as the probability that a packet is lost, versus the throughput. And then the answer is yes, there is a formula which, like anything done in this domain, is very approximate and is given here. Theta is the throughput, L is the RTT, is the MSS, T is the RTT, C is a constant, a magic number that comes from the analysis you can look up in the lecture notes, and Q is the loss rate. Of course, it's very approximate and is probably not true if Q is extremely close to 0. And it's called the square root formula. So this captures practically everything we would like to know about TCP. We can interpret TCP as a utility maximization function. That's one way. But another way to interpret it is to look at this formula and say, if you receive a loss rate that's significant, significant means the average packet loss will be close to 1. Then the rate that you will receive is practically equal to 1 packet per round trip time, which is the minimum window, minimum congestion control window that TCP will give to you. If the Q is close to 0, so you don't lose anything, then the theta is infinite. Of course, this is the maximum theta you can get, assuming you have unlimited source speed. And we see also that the bias of the round trip time comes here in this formula as a proportional term. So if you have two connections that have the same Q, the same loss rate, then the throughput they will receive is inversely proportional to the round trip time. This formula is the simplest and probably the only usable one. People have developed it ignoring slow start and fast recovery and other bells and whistles of TCP. Other people have developed other formulas that are a bit more complicated and which we can regard as second order approximation of this one, which is a first order approximation. This can be used to do things like we've seen before, that S1 will receive less than S2. Can we go one step further and say what's the ratio of the throughputs of S1 and S2? Sorry, S1 will get more, I think. I close the poll in 5 seconds. And the correct answer is the majority vote, 7/3. Now it's a simple primary school proportionality computation. The throughputs will be inversely proportional to the round trip time, so they will be inversely proportional to 3 and 7, which gives 7/3. So it's a significant, those numbers are quite realistic, they happen. So just by having 60 milliseconds somewhere instead of 20, just because you're behind a NAT or behind a network of a certain type that has a bit more a few more milliseconds of delay, you see that the throughput may be less than half for you compared to someone else. So think about that when you will compute the throughput that you see when you're downloading video files or in Lab 5 when we do those things. Of course, people have been worried about those bugs on TCP. The first about RTT, they're not worried because most people don't understand. They think it's good to have this bug, because long RTT is a symptom of using more of the network, so this will not be fixed. But the more severe thing is losses being interpreted as the congestion signal. That's a serious problem. That's why TCP works not so well when you have Wi-Fi and also satellite links. Of course, we can fix the problem by using other mechanisms than TCP for transporting data over satellite links. And Chokrolai, for example, has been famous for the coding schemes he has done that are an alternative to TCP. But this is practically not deployed by anyone. Instead, there has been an attempt to fix the problem by imitating the DEC bit. Remember, the DEC bit is a bit in the packet header that says there is congestion in this router. Instead of killing the packet, you mark the bit. Right? So this has been done and has been defined 20 years ago. It is not very, very much deployed, but might, like IPv6, be more deployed in the future. It's called ECN, Explicit Congestion Notification. So the idea is to exactly imitate the theoretical model we have seen before, which itself was inspired by the DEC bit, and mark one bit in a packet when a router sees that its buffer is full. So here's a small animation showing how it would work. I'm showing here a source, and this router with the red circle means it's congested. A router can see congestion by counting, for example, how many packets there are in a buffer. And a smart router will see congestion before the buffer is full. A non-smart router sees packets being dropped when the buffer is full. A non-smart router can start raising an orange flag somewhere when some buffers are more than 50% full, for example. And S is sending to destination R. So ECN works in the following way. I'm showing the IP header and the TCP header. Of course, we don't want routers to look at TCP header. At least originally we did not want. That's the layering principle, the founding principle of TCP-IP. I say in principle because we've seen that in reality many routers look at port numbers and TCP headers and things like this. But certainly you would not like to force all routers to look at all TCP headers. So we will mark the congestion in the TCP header in the following way. When the packet sorry, I was completely wrong. The router does not want to interfere with the TCP header. So when the router goes via this router, the router will mark one bit in the IP header, one of those bits that we have not yet discussed in detail. Well, it's time now to look at it. There are two bits in the IP header of IPv4 or IPv6 that are called type of service bits that are for ECN. Y2 I'll talk about in a second. Right now we need to imagine there's only one. So if a router sees buffers that are a bit full, it will mark this packet header. If the destination now needs to cooperate for this to work, the destination operating system will see that some of the packets for this TCP connection had this ECN bit marked in the IP header, and will echo this back to the source, because of course it's the source that should do something, by putting in the TCP header now of the reverse flow some indication that there was congestion. Now when S receives this, S will see in the TCP header that there was congestion, and it will have its congestion window. And if we do that smartly, if all routers do that before the buffers are full, you will not drop packets because of full buffers. You will not drop packets because the sources will reduce the rates here. So this will relieve congestion here. And for everybody, it's nicer. It's nicer in particular for the source because the source gets the same signal as before. If we don't have ECN, the router would simply drop the packet to give the signal back to the source that it should reuse. But dropping a packet for a TCP source is not a very pleasant thing to do for the source because it will need to retransmit and play with a number of things. So here, nothing is lost. The job of the source is simpler. And this is how it works. Now, concretely, it's a bit messy. There are many, many bits that are used for that. There are 2 bits in the IP header and 3 bits in the TCP header, when in my cartoon we need only 2 bits. Right? So why do you need more? We will not see in detail. There's more in the slides, but I don't want to explain that in detail. There are several things to care about. The first thing is it's not sufficient to just have a bit here, because that would be sufficient, and it was sufficient in the case of the DECnet. In DECnet, there was only 1 bit in the IP, in the digital IP header, because all sources were implementing the DEC bit. Now, in the internet, you have sources that implement ECN and sources that don't. You have TCP implementations. In fact, most don't react to ECN. So what happens if this router does this job here and the source doesn't react to ECN? Then what will happen is it will have a nicely marked packet, will not reduce the window by 2, will continue sending until really bad things happen, losses, and only then it will decrease. What would happen in a network where you have both ECN and non-ECN capable sources? Who benefits more? The non-ECN sources. Because the ECN sources, they will reduce their rates more often. They will make space for the non-ECN sources. So it's like being very polite in a traffic jam. You let everybody go, but at the end, if you don't move very fast, right? So that's exactly what will happen. ECN sources competing with non-ECN sources will receive much, much less throughput because the non-ECN sources react only to losses. So, and that's the source of the complication. That's why we have so many bits here. So how do we fix that? Well, we fix it first by saying in the IP header, you put a bit that says whether this source is taking ECN seriously. Is ECN capable? And if this bit is not present, the router will see, oh, this is a source that is not taking ECN seriously or is not ECN capable. Therefore, I will not, there's no point marking the bit here. I will drop the packet instead. So a router will analyze whether this bit is present. If it's not present, it will drop the packet instead of marking. So we reverse the logic. Then it's better to be ECN compliant than to be not ECN compliant because you will receive marked packets instead of lost packets. Of course, it's not sufficient to believe I mean, if you were playing with your Linux implementation of TCP, then you can declare that you are ECN compliant and you don't run ECN. Whenever you receive a marked packet, you don't. We could say you can also disable congestion control, and then you will get more throughput. And it's true. So we can argue whether it's really necessary to police the ECN capability, whether it's necessary or not, but it's done. So there are more bits, random bits, that are put here in the IP header to allow the destination to test whether the source is really responding to ECN or not when it declares that it is ECN capable. We will not explain why in detail, but there are 2 or 3 slides that explain that in detail. So if we summarize how the internet works with TCN, assuming ECN is used and there is no packet lost, here is schematic evolution of the window size of a TCP connection, and I'm asking you to put the correct labels 1 and 2. CA stands for congestion avoidance, SS slow start, MD multiplicative decrease. Which is what? Okay, it's time to close because we're timing out anyhow. So I'm closing the poll. And of course, the correct answer is 3, congestion avoidance here, and multiplicative decrease there. And of course, there is no slow start if you run ECN. And there's no need for all those complicated fast recovery and slow starts. So it is a clean implementation of AIMD when you have ECN. Voilà, we do a break and we resume in 14 minutes. Active queue management. Those are things that are visible if you configure a server or a router. So what is active queue management? It's practically synonym to RED, which means random early detection. RED is simply the mechanism by which an ECN router decides to mark a packet. I mentioned that you look at whether the buffer is full enough, which is more or less what RED is doing, plus it adds an exponentially weighted moving average of the buffer size. So instead of looking just the instantaneous buffer content, with RED we look at low-pass filtered value of this, which is expected to be an approximation of, if we would be in stationary regime, what would be the average buffer size. That is this value here. So now you take this value and put it on the x-axis, and on the y-axis you will obtain a number between 0 and 1, which is the probability of marking a packet. So with RED, we don't systematically mark a packet, i.e. with probability 1 when the threshold is exceeded. We do it when we exceed this threshold, TH max, but in between, in particular in this zone, we mark with a given probability. So if this estimation of the average buffer size is very small, you do nothing, you don't mark anything. If it's very large, you mark all packets, and in between you mark packets with a small probability. Which means that if there are many packets and many flows, you will give a small feedback to the sources, to a small fraction of the sources. And the idea is that by doing that, you are smoother than simply by being 0, 1, which is essential for a nice and stable operation of the network. This specific method, there are zillions of other methods that have been proposed that are more sophisticated, but they are necessary if we implement ECN. Now, they are also implemented even if we don't implement ECN, which is a bit paradoxical and sometimes hard to understand. RED is very often implemented in routers, even routers that to non-ECN flows. And the reason is, the primary reason is this one, is to avoid constantly full buffers. What's the phenomenon here? Assume you have a number of sources that are competing for a bottleneck and you don't use ECN and you don't use RED. What will happen? then the bottleneck output buffer will fill. And when it's completely full, you will start dropping packets. When you drop packets, you send negative feedback back to the source, so you oscillate between, you will have this oscillating behavior that we have seen many times in the simulations of how sources work. Now, if your buffer size is very large, what can happen, and it's easy to reproduce by simulation, is that the buffer content will not become zero, because the buffer is full. You give a signal to source that they have to reduce. They reduce the rate. Therefore, the buffer drains a bit. It becomes less full. But since the buffer now is not full, you don't drop any packets, so the sources will will increase again. So the sources will constantly be trying to test the water to be close to capacity. And in average, the network bottleneck is full. It's working at 100% capacity. If you operate a buffer at 100% capacity, then it will be practically full. So in other words, when it drains a bit, it gives a signal to sources that they can increase again, which means it will fill up again. So there are many cases that have been seen where this phenomenon does occur. So you will have a large network buffer that is oscillating between 90% full and 100% full. If you have that, what happens in fact? Well, it's like if you had only 10% of the buffer. So you could say, well, it's because your buffer is not good. You should put a smaller buffer, which is true. There is an optimal buffer size in any queuing system, which is not necessarily the larger, the better. If the buffer is too small, you drop packets because too often. If the buffer is too large, you start filling it up, and then the fluctuations visit only a small fraction of the buffer. Plus, if that happens, then the buffer is 90%, between 90% and 100% full. That translates into something non-desirable. What? What is the non-desirable behavior? Yes? Latency, delay, exactly. If you have a buffer with 1,000 packets that is full, that is always has 1,000 packets, whenever a packet arrives, it needs to wait for 1,000 packets to be delivered, which may be seconds, even on a high-speed link. So this will add into delay. So delay is not good. We don't like delay for a number of reasons. So in order to avoid that, it's a better idea to do something like RED, which means having the same curve as before. And as soon as you start seeing that the buffer fills with a small probability, you will send a signal back to the sources before the buffer gets full. So, and it has been shown that this works well. It manages buffer to be almost always empty, except for once in a while the buffer can do an excursion into being full, but it will quickly become empty again, which is the normal behavior you expect for a buffer. A buffer is like an insurance. You expect it to be there to help you if something bad happens, but you don't expect to use it all the time. Otherwise, it's not useful. So this is why you will have this red stuff often deployed, which is paradoxical. It's saying, if I am running a buffer, I should not necessarily, there are cases where it's better to drop a packet than to accept it, even if there is space in the buffer. The reason for this paradox is because we have a coupling with congestion control. We have sources that react to buffer, to losses in the buffer. In a network where all flows use ECN, which today is hypothetical. Perhaps in an enterprise network you can enforce this, but in the internet we're not yet there. But assume perhaps in 20 years everybody in the internet will be using ECN. What do you think will be true? I close the poll in 5 seconds. And the correct answer is 3. There is no packet loss due to congestion in routers, if everything is well dimensioned, if the parameters of RED are well chosen. But there might be losses not due to congestion, for example, due to wireless channels. And there can be losses due to congestion somewhere else in switches. Switches are like routers, packet, they are queuing systems. Now the switches, in principle, they don't look at the IP header, they don't manipulate the ECN bit. So if you have a switch output buffer that is full, you cannot do anything except lose the packet. Except if you have a switch that also looks at the IP header, but then it's which is possible, but in principle, it's doing a bit more than layer 2. So that's the state of things for congestion control. Now, some people have found that the current, so congestion control based on AIMD, if you have AIMD plus ECN, then the network will start working well, except for the losses due to wireless that somebody needs to fix someday. But there are cases where this doesn't work well. This is showing how AIMD works if you have what is called a fat network, which is a network that has a very, very large throughput and also large, not necessarily large, but non-negligible latency. That's the internet in 20 years. In 20 years, we will have gigabits per second everywhere, including on wireless links. And we will be transmitting gigabits per second just to, instead of looking at a text that would take 2 bytes or 2 kilobytes, we will watch a video that will say the same thing, but in gigabytes instead. And this is, well, I don't see any number here, so yeah, that's the interesting thing. Those are the numbers it takes on such, if you have a link at 10 gigabit per second, in order to, when we do additive increase, multiplicative decrease, the window size oscillates between a target value and half the target value. Right? And those values, in the case of those numbers, are huge. So we're talking of extremely large, hundreds of up to 100,000 packets. How much time does it take? Now, if you're gigabit per second, you can say that goes very fast. But no, the time is in hours. Right? So while you're transferring, you see your rate increasing on the little text that gives you how many gigabit or megabit per second you're getting, you will see that it takes hours to do this. So TCP does not work well for those networks. Of course, those networks are still not very dominant. I mean, you seldom get 10 gigabit per second for one TCP connection. But if that happens, you need to fix things. So how do you fix it? Well, you can change the parameters of TCP. The additive increase, you could make it larger. Instead of making 1 per round trip time, you could make it larger. And this is more or less what is done in several, I mean, there's a flurry of competing versions. The most widespread is Cubic, which is implemented in Linux, most Linux versions. And the way it does it takes a target RTT of 100 millisecond, and it says when the RTT is 100 millisecond or less, then it behaves like we've seen IIMD. When it's above, it becomes more aggressive after the window has reached the value, a minimum value. So there are many, many details in Cubic that we will not see. If you're interested, it could be a research exercise for next year. Another issue is what happens if you have non-TCP applications. Then the first answer is you should not. You should run everything on TCP. But there are good reasons for not using TCP. Do you know any of them? Well, here are some are given. If you have one-way flow, for example, sensors that send data to a sink. You have also multicast applications for TV distribution that run UDP. And perhaps if you do real-time video, like Skype, you might not want to do it with TCP. Because with TCP, when a packet is lost, you retransmit it, and that may take several hundreds of milliseconds until the loss is repaired. If you want interactive audio, primarily, you would like the round-trip time to be less than, let's say, 200 milliseconds. If it's above, then you have this half-duplex effect where you talk, and then you see the other person wait until the other end has answered, and that's what you see that on TV when people talk about remote locations. It's because the round-trip time is too large. That happens if you use TCP. If you use UDP, you can avoid this by having smart coding schemes. If a packet is lost, you don't repeat it. You just use the coding scheme to mask the loss. For example, if you're transmitting video, you can interpolate between the previous frame and what you have received now. Same for audio. You can put a little interpolation into the audio, so there will be distortion, but not delay. So this is let's say, the state of the art for interactive multimedia applications. Now, if you do that, if you have a lot of them and it's high quality video, you start having flows that are not congestion controlled, and we have seen the theory 2 weeks ago. You should not do that in a complex network. You can cause congestion collapse. The theory today, the dogma of the internet is all those applications should be TCP friendly. So they should implement a protocol that imitates the rate that TCP would compute for them. One such protocol is called TFRC. There are other ones. It's implemented in many interactive video applications. It does not do TCP like with a window, but it computes a feedback, which is how many packets were marked by ECN or were lost, using special overhead in the protocol. For example, the so-called RTP, real-time transport protocol, which is not a transport protocol, but an application layer protocol, puts statistics on packet losses. So once every so-and-so, for example, once every round-trip time, the video application sends back to the source a feedback on how many packets were received since the last feedback has been sent, and the packets are numbered by the application, so you can infer how many were lost. Then the TCP source adjusts the rate. How does it adjust the rate? There would be several ways to do it. It could do AIMD, but here, most of the time, the idea in those protocols is to use the TCP loss throughput formula. It says, I have seen a loss rate Q. I compute a rate X, which is now a true rate, not a window. Things like multimedia coding can have an associated rate. So you change the coding rate. If you can see that if you try to do an MP3 with in your preferred multimedia library, then you can choose the rate. So this application will do this. It will update the rate in order to find the nearest match to what the TCP loss throughput formula would give. It's a very contorted way to be TCP friendly. It works only approximately. There are many biases, estimation and statistical biases, but at least it provides a form of congestion control. If the network is severely congested, all those multimedia applications will have also a very small rate, so they will not contribute to causing congestion collapse. So that's another dimension that we find in the internet. Yes?
And what about BitTorrent protocol?
BitTorrent uses TCP. So the connections between the peers are with TCP. So it's congestion control. Anything that doesn't have an urgent need for UDP should use TCP. So most things use TCP. Even when you watch TV over YouTube, it's with TCP. Even Skype sometimes uses TCP if it sees that there are too many losses. But if you use TCP, you'll have a delay that is not extremely small. But if you're watching YouTube, you'll have a delay of a few seconds, which is in your playback buffer, which is okay for watching. Now, there are still applications and there are cases where you don't want to use TCP and you don't want to use congestion control. For example, If you're doing a smart grid application, you have thousands of PMUs, those are sensors, that sense measurement every 20 milliseconds. They send one packet every 20 milliseconds, so they have a constant rate. You don't want to adjust the rate. That's your, I mean, you've invested into this infrastructure. They do their job, and their job dictates that they have a constant rate. So you still have environments where you have applications that must send at a non-controlled rate. Of course, if you just use this in a network without any caution, we've seen there can be congestion collapse here. So if you have things like this, you need to engineer your network. Engineer your network, that means know the flows and what rate they are giving, they are producing, and put the capacity on all the links such that there will never be congestion collapse. You do it by static dimensioning, not by requiring that the sources adapt their rates. Of course, we don't do that in the internet. We don't want to have to be controlled. I don't want to have to declare, now I go and watch a video, therefore I need to get an authorization to get that rate. We don't want to do that in the internet. But in some environments, industrial environments in particular, you may have a need to do this. If you do this, you will typically use differentiated treatments of different flows. A form of it can be simply priority. Assume you have your network with your streaming devices that each stream at a constant rate. You know how many devices you have, so you know which capacity you have to give to those. But on the same network, you may still have TCP that's working because, for example, you're doing a software update on a PMU, you're downloading something into it that uses TCP. Or you may use your network for other things, for current business that everybody does. So one way to do this, to support such environments, is to do priorities. There are zillions of forms of priorities, but the simplest form to think of priority is the absolute priority, the non-preemptive head-of-the-line priority, which consists in saying, when I must be able to categorize flows, have red and blue flows. How can we classify flows? Typically, routers will do it by looking at predefined rules that look at the IP addresses and port numbers. So again, this is not for the global internet. It doesn't scale to huge amounts of things, but in industrial or private environments, you can do things like this. We do this, for example, on the network of EPFL for voice. As you know, telephony today is an IP application, but the IP packets of voice are given priority over all other IP packets. Not of you and me if we use Skype over our smartphone, then it will be a standard IP packet. But if we use the EPFL telephones, there must be one somewhere here, no, not in this room. So if you use the special telephones that are special equipment that are on special VLANs, and all the traffic that originates on those VLANs is treated as being high priority. Of course, you don't expect a phone to generate all of a sudden a gigabit per second. So you know the max rate at which it transmits, which is very, very small. Telephony is a minuscule application in terms of volume, but you want the delays to be small. So if that happens, you can give priority, treat telephony as red. You give priority to the red, which means when there is in a router or a switch a packet that comes, if it's a red packet, it is immediately put in the queue, and the router will serve the red queue until it's empty. Which means that if in between there are blue packets that come in, they will be queued in the blue queue, and they will be served only if there is no red packet waiting. So that's absolute priority. As the very irritating priority you see at the airport when you're queuing in the non-priority queue for passports or for security check, and you have a few people coming with high priority. If that happens, you will never be served until this queue is empty. That's the strict priority. If we do that, of course, the red flows will see a network where there is. So if I do that in this example, the red flow will see a network which is only for them. And if I have only two sources that send each at 1 megabit per second to this destination, then because the bit rates are larger here, there will not be losses, there will not be congestion collapse. What happens to the low priority? Well, the low priority, in this simple case, will simply see a network where there is variable capacity, and which is the link capacity minus whatever the red are sending. And here, because the red are sending at constant rate, for the blue, it is as if I had a network at 9 megabit per second on the first link and 8 on the second, 8 because I have two flow of 1 megabit each. So by doing that, I have separated traffic. That's a form of traffic engineering in a network. If those are using TCP, then they will need to share these bottlenecks. In fact, if they do use TCP, which rate will they get? So PC1 and PC2 are using TCP with this RTT. How much will they get on this network? I close the poll in 5 seconds. And the correct answer is the majority for each. Well, to understand why, we can do this analogy and say those two sources, PC1 and PC2, are implementing TCP over a network, which is this one. The first link is 9 megabit per second. The second is 8. Now, what does TCP get there? The simplest way is, well, I know TCP is between max-min and proportionally fair. Now, what is the proportionally fair or max-min fair allocation for this? The max-min is easy to get. We have two links. The first link at 9 megabit per second gives the constraint x1 less than 9. The second at 8 gives the constraint x1 plus x2 less than 8. Now, if x1 plus x2 is less than 8, automatically x1 must be less than 8, so it is less than 9. In other words, the first constraint is irrelevant. So from the viewpoint of any kind of fairness, the feasible region for the rate is entirely dictated by the second link only. So I have only this constraint. Max-min fairness, then we increase. We get 4 for each, and then we stop, so 4, 4. But proportional fairness is the same also, because there's only one single link. If I try to deviate from 4, I will decrease x1, and this is, because it's concave, I will decrease the total utility. I can also reason directly. TCP solves a utility function. And if we want to maximize that, because we solve something that in x1 and x2 in the same utility function, because they have the same round trip time, therefore it must be 4. Priority queuing is sometimes used, but in fact, instead of priority queuing, we more often use what is called something like class-based queuing. There are very many options of this, and Cisco has many different ways of implementing those priorities. But in the Linux environment, the most useful and most used one is called class-based queuing. Class-based queuing is practically the same as priority queuing, but tries to mitigate a number of negative side effects. In particular, the side effects could be if the high priority flows start misbehaving. In the previous example, we assumed every PMU streams at 1 megabit per second, which is probably what they should do. But bugs exist, as you know. A PMU is a Linux system. It can have a bug, and for whatever reason, it can start transmitting at full rate instead of the rate it should be transmitting. If that happens, because we have no congestion control on the high priority, we might have congestion collapse in the high priority class. And because high priority is before the rest, there will be congestion collapse for everyone. So if you have one PMU that sends at 20 megabit per second, then it will fill the network, and the network is dead for the rest, which is not okay. So you still want to protect yourself from things like this. This is what is done by class-based queuing. With class-based queuing, we classify flows in classes, like we did for priority queuing. We guarantee a rate to each class, And then there are two possible options. Either this rate is guaranteed and you cannot send more than at this rate, or you can send more than at this rate, but only if there is spare capacity from the other classes here. Let's see concretely on one example. In this network, I have PMUs that stream at 1 megabit per second. So I need 2 megabit per second on this link here, for example. I am a good engineer. I always add 20%. So I will allocate 2.5 megabit per second to this class on the second link. And if I want to be very simple, I allocate that everywhere. For the second class, I will allocate the remainder, 7.5 megabit per second, but I will allow it to borrow. Borrow means if those PCs are sending more than they can as long as it's available, which means as long as the red flows are not sending. But the red flows cannot borrow, which means I'm putting a cap, I put a limit. If they want to send more than 2.5 megabit per second in total, they will not be served. It will build up in the queues. Of course, my PMU will have a problem. If one of the PMUs is sending at 10 megabit per second, for example, it's a bug. It should not. So the red queues will start building up, and there will be lots of losses for the PMUs. But at least the rest of the network, the blue classes, will continue to work. We'll see a network at 7.5 megabit per second, which will, for example, be useful for me to log into the PMU that is streaming at a higher value, reset it, and do a patch of some kind to gain control back of it. So that is the classical use of this. Same question as before. Now, I assume this setting, PC1 and PC2 are using TCP to transfer the data. PMU 1 and 2 are using 1 megabit each. How much will PC1 and PC2 get? I close the poll now. And of course, it's the same answer. In fact, here there's no difference. Everything is exactly the same. The difference in class-based queuing will be visible only if the PMUs are misbehaving or sending more. So the fact that I have guaranteed 7.5 megabits per second to those doesn't mean they get 7.5. They will get the 8. But if the PMUs, for whatever reason, would be streaming too much, then they would still get 7.5 megabit per second. Voilà, that's all for the theory part of congestion control. It's an unusually long module, but I tried to separate between the theory and the practice, so between the theory 1 and theory 2, let's say. So the important things are to understand what the problem is, as usual. The solution in the internet, which is additive increase, multiplicative decrease, and all the other bells and whistles we have discussed now. And without further ado, we move on to the next topic, which is BGP. Are there any questions on this before we move on? No? Then let's go.